Okay, don't let the soothing music fool you. We're going to start Monday morning with some math. Let's make sure we get enough material under our belt that you can start the problem set that is due on Friday. Okay. So jumping right back into complex numbers that we started talking about last time. Let's get everything we need to know about them out on the table. So we saw that we could represent complex numbers as the sum of real and imaginary parts, and that they are represented in a two-dimensional space. Then usually we use the x-axis for the real part, y-axis for the imaginary part. So a real number is just a point on a number line. Complex number is a point in this two-dimensional space. And for example, we can consider a couple points here. Here we have 2 plus 3i. If we label this as 1, and that's I minus 1 minus I, then that's going to be up 2 plus 3i, something way up here. And negative 1 plus I is going to be this thing right here. Now we already saw, of course, summing them is just very natural. You just sum, just like you sum any vectors, because the real parts add and the imaginary parts add. So we know that this is 1 plus 4i, which of course is going to be way up here. So this is the sum. Oops, what's going on? All right. Now, we also know that unlike general vectors, complex numbers, there's a natural definition of a product, of multiplying or dividing them. And we, as we did last time, you can just use your arithmetic we usually do for multiplying binomials to figure out what the answer is when you multiply these. I'll just write the answer. We won't work it out because that was too easy. We've done that before. So this product here of these two is going to be minus 5 minus I, which we see as this point over here. So this is the product. And we'd like some sort of intuitive understanding of how the product ended up over there. The sum was very intuitive. We could just, for the sum, we could just take these two vectors and put them end to end the way we are used to adding vectors. And how do we get the product? I know many of you know this, but if you don't, it's kind of fun to see how. All right. And of course, the key comes from polar notation, from using polar coordinates for complex numbers. All right. Let's give ourselves some space. So we see that if we that we can actually represent any complex number as a positive real number times e to the I times some real valued theta. All right, and Euler's identity says, well, the a we'll just keep a. It's just a constant multiplied by both things, and we'll replace e to the I theta with the identity cosine theta plus I sine theta. Now, this means that. Of course, we see that cosine theta and sine theta are lengths of a right triangle. So we have a new way of thinking about points in the complex plane. Again, here's the complex plane. We've got real, we've got imaginary. And we have that a point here is if we consider the length, the distance to that point from the origin to be capital A, and the angle to the real axis as theta, then this point is exactly a e to the I theta. Okay, so that's the polar representation of a complex number. Of course, we see that exactly because of this equation here. Right? Okay, well, this is good news because multiplying numbers of this form is much easier than binomials. Okay, same with and dividing. All right, so for example, if we have two numbers represented in polar representation, a1 e to the I theta 1, and we want to multiply that by a2 e to the I theta 2. Of course, this is just going to be a1, a2 e to the I theta 1 plus theta 2. So the magnitudes, the lengths just multiply and the phases just add. That's what we'll call these things here. We'll call this the magnitude. And this is the phase. Great. So we have so if we convert everything to polar notation, then multiplying is trivial, and dividing is trivial too. Of course, dividing we would just do the opposite. So if we were doing, let's do this, a1 e to the I theta 1 over a2 e to the I theta 2. Of course, we just get a1 over a2 e to the I theta 1 minus theta 2. Okay, so it's very easy. Of course, adding and subtracting now is not going to be straightforward in polar coordinates. That's easier in rectangular coordinates, okay, in the original coordinate system we were looking at. So they have their advantages and disadvantages, but we're often going to be interested in multiplying, so this will be very useful representation. If we go back up to our example here, and we say, okay, now we know how to interpret both of these things. The sum, again, was just the sum of these vectors gave you that sum. The product was simply, we can think of as by considering the angles. This new line here, the result of the product, the length of this line is the product of these two lengths. Okay, this one is just a length just slightly more than 1. It's the root 2, right? And so root 2 times this length should be this length. And the angles also, we have, there was an angle here, there was an angle here, and the sum of those two angles should be this angle all the way over to here. Okay, the phase is added. Right, so in fact, multiplication is very intuitive as well for complex numbers. Okay, let's see. You can now talk about, for example, square roots or cube roots or high-order roots of a number and understand more than you did with just real numbers. For example, consider the cube root of -1. All right, this is something that you don't need imaginary numbers to handle. What's the cube root of -1? It's -1. All right, so far so good, but there are other cube roots. Now that we are talking about complex numbers, we can find other cube roots. In fact, there should be 3. Okay, just like there are 2 square roots of positive numbers, the plus and negative side, there are 3 cube roots. And we can identify those using our intuition and our understanding of complex numbers. One way to do that is to represent -1 as, let's say, using our polar coordinates, complex numbers. So we need a positive number, plus 1, times e to some phase. It turns out e to the I pi, okay, will be negative 1, right? E to the I pi, just think of the polar, just think of this space here. If you take 1 and you multiply it and you add a phase of pi, you get over here to negative 1. All right, so e to the I pi is negative 1. And what we can do here is, if we take a cube root then we should take this whole thing, 1 e to the I pi, to the power of 1/3. Okay? And it's a product, so we can just split that in. Of course, 1 to the 1/3 is still 1. But e to the I pi to the 1/3, you bring the 1/3 in, it's pi over 3. Okay, so this is a complex number that is exactly right here. Let's mark where 1 is again. This complex number is right about here. So this is e to the I pi over 3. Let's mark where negative 1 is. Of course, negative 1 is over here, and that's the number we're trying to take a cube root of. And you maybe can see that e to the I pi over 3 is a cube root, because if we take this number, think about it in polar coordinates, its length is 1, so when you cube the length, nothing happens. But if you multiply this by itself 3 times, the phases are going to add 3 times, right? So when you square it, you're going to end up over here. And when you cube it, you do it one more time, you're going to end up over there at negative 1. So there's a 1 cube root, right? How do we get what we already knew? We knew negative 1 was a cube root of negative 1. How do we get that? This seems to give us a different answer. Well, the reason we can get 3 cube roots is because you can actually represent negative 1 in a number of ways, all right? We can represent it as we have up there. I'm going to drop the 1 because the 1's not really doing much for us. So you could represent this as, for example, e to the I 3 pi. Because you can go around the circle more than once. These are exactly the same number. Now when I do my derivation, I'm going to get e to the I pi. I'm going to get negative 1 as a cube root. Where would the third cube root be? Yeah? Perfect. So it's down here. That's the third one. Okay, and there's this nice pattern to it, which is that happens in general for roots. So you see that, again, this has an angle of, this you can write as e to the negative pi over 3. And if you add that phase 3 times, you get e to the negative pi. That's the same as e to the pi. Okay. And another way, I mean, there's so many ways you could have gotten there. You could have gotten there by saying, well, let me make that e to the negative I pi. Okay, and then do this derivation. Or you could say, let's make that e to the I 5 pi. We did pi, we did 3 pi. We could do 5 pi, right? Then you'd get a positive angle. The answer you'd get after taking the cube root would be 5/3 pi, or would it be? Yeah, 5/3 pi, which is actually going to be yep, it's going to be the angle you get from going all the way around here. So it's just the same angle represented with a positive face rather than negative. So you see there's some ambiguity in polar coordinates. You could always add a 2 pi into the face. So we could say, just for your note's sake, and we could also say that equals, I'll do it with the positive one, although it's perfectly good to make it negative I pi. Therefore, cube root equals e to the I 5/3 pi, and that will be the same as e to the negative pi over 3. Okay. Oh, I. There needs to be an I in there. All right. Good. complex conjugate. So the complex conjugate is very easy to understand. You just negate the imaginary part. So we usually use a star to say the complex conjugate of a number. For example, if this is your number, the complex conjugate is just going to be 5 plus 3i rather than minus 3i. Okay? The complex conjugate reflects across the real axis in the complex plane. So if your number was here, let me use blue. If your number's here, then the complex conjugate is down here. Right. Okay, and complex conjugates behave nicely in things like products, for example. So if you have first of all, if you have a number in polar coordinates, a e to the I theta, the conjugate, as you can see from the graph, is just going to be a e to the minus I theta. Okay, you just negate the phase, so conjugate just keeps the magnitude the same, makes the phase negative. For products, if you have any complex numbers x times y, and you conjugate them, you just conjugate each one and multiply. And if you have an exponent with a real base like e to the x, where x might be complex, okay, and you conjugate this whole thing, that's also just e to the x conjugate. So that's nice. Okay. Don't confuse my stars and my x's. All right. Now, we can give a definition for extracting a real part of a number using these conjugates. Okay, so the real part is just what it sounds like. You just drop the imaginary part. So for example, if we have things represented in rectangular coordinates, real part is obvious. The real part of this number is 5. All right. You also can talk about the imaginary part. And the imaginary part of the same number is just -3. We drop the I as well. Okay. So the real part, the imaginary part is real. All right. You don't keep the I there. You end up with a real number. Okay, but in general, we can give a formula for getting the real part of a number. The real part of x is always going to be x plus x conjugate over 2. You can check these examples up here and see that works. All right. The imaginary part of x is going to be x minus x conjugate over 2, although we need an I. We get rid of the I. Over 2i. Okay. Now from this we can actually get a new version of Euler's formula, one you probably are familiar with, but it's different than the one I've written already. Let's use this formula as an example and say so we have e to the I x, right? Euler's identity says it's cosine of x plus I sine of x. All right? And of course, from this identity, we know the real part is cosine of x, and the imaginary part is just sine of x. Right? So let's use the formula above, and let's say cosine of x. As we know, that's the real part of e to the ix, but let's just get this in a different form. That means the real part of a number is that number plus its conjugate over 2. So 1/2 e to the ix plus e to the negative ix. Okay, so you've probably seen it written that way. Sine of x can be written as well as sum of two complex exponentials. So these things here, we just call these complex exponentials. And sometimes it's useful to represent trigonometric functions in terms of complex exponentials. We'll see the use of that here. In fact, you can derive most of the trigonometric function identities that you're familiar with from this simple relationship. If you express them instead as complex exponentials, then multiplication is much easier. So things like sine times cosine, what does that equal? You have an identity for that. You can derive that very easily by just replacing sine and cosine with these formulas and doing the multiplication that you already knew how to do with exponentials. All right. Now we'll also use the conjugate to define the magnitude of a number. Okay. So the magnitude of a number, we already said in polar coordinates, that's that coefficient out front. We call that the magnitude, right? And it's the length. It's the distance of your complex number to the origin. Well, this is a generalization of an absolute value. And we'll use the same notation we use for absolute value to represent the magnitude. So the magnitude of a number x is, by formula, the square root of x times its conjugate. So we should first check that this makes sense. Suppose that x is expressed in polar coordinates, right? So we would have, generally it's a e to the I theta. Then that means that x times x conjugate is a e to the I theta times a e to the negative I theta. All right. Now multiply these, you get a squared e to the I theta minus theta, that's a 0. So this whole thing can be ignored because this is a 1. Right. You get a squared. Take the square root, and that equals a. And that's what we said was the magnitude. Okay, so this formula checks out, but this will work even if x wasn't expressed in polar coordinates. If it was in rectangular coordinates and you want to know what is the magnitude of this number, that's how you can calculate it. In fact, we should also let's also do it for rectangular coordinates to see how this actually simplifies. So there we have something like, let's say x equals a plus ib. Okay. Now what's the magnitude then of x? Square root of a plus ib times a minus ib. That's the conjugate. And if we multiply that out, we're going to get that the plus and minus parts, the cross terms cancel. Right? So we just get square root of a squared plus, or minus, let's say, minus ib squared. But I squared is negative 1. So this equals a squared plus b squared. Okay, so the magnitude of a number, as you would expect, you can just square the real part, square the imaginary part, add them, and then take the square root. Of course, if we think about it, we already knew this, right? Because you know how to represent, you know that in the complex plane, a number is represented by the two coordinates, real part and imaginary part. And if we wanted the distance, we know how to calculate a distance. This is the formula, right? But it was good to check. What about the phase? So the phase of a number can be calculated as well. Let's see, we did magnitude here, so let's go down and do phase. And So here we would have that theta is expressed as an arctangent. You just get this from the trigonometry of how we represented things in polar coordinates. It's the arctangent of the imaginary part of x over the real part of x. Okay, now there's a little bit of ambiguity in the arctangent. So you actually have to add pi here depending on whether or not the real part of x is negative. Okay, so we use this notation of 1. That's an indicator function. It says only do this if the following statement is true. If the real part of x is less than 0, then this becomes a 1. Otherwise, it's 0. So what this is saying is, if the real part of x is negative, you better add pi to make this correct. We'll see very easily why this is true. Notice that two numbers, if we're trying to find the phase of a particular number, right? It has a real part here. This is the real part of x. And this is the imaginary part of x. All right, well, we would divide them and do an arctangent. But so we want to get this angle theta. But notice that any line with that same slope is going to give the same imaginary part of a real part. So for example, this number here, any number along this line here would also give this same argument, imaginary over real. Okay, but that's obviously a different phase. And that really comes from the fact that we defined the magnitude to be positive. If you could define the magnitude to be negative, you could say these all have phase up here and they're negative numbers. But the magnitude's positive, so we have to account for this side of this line by saying that the phase, it's a different phase. It has a pi added to it. Okay, so of course, usually arctan is defined to always return values between pi over 2 and negative pi over 2 in this range. Okay, that's the usual definition for arctan. So when you're in this range, you just have to check for it. Am I over here? And that's when the real part is negative. Then I'm going to add pi. So now we actually see how we could convert a number from rectangular coordinates to polar coordinates. Okay, we could convert it by just calculating the magnitude and the phase of that number. Once you have the magnitude and phase, you have its representation in polar coordinates. Right? And we have a formula for both now, explicitly. Okay. So that's roughly it for complex number review. All right. And now I'm going to go over some things that relate more towards signals, or in other words, functions. So let's start by talking about a simple property of a function that sort of mirrors what we already saw about complex numbers. All right. So we would say that a signal, when I say signal now, just think of any function where the domain is the real numbers for now. It can be classified as being odd or even. They're not. I don't mean every signal can be classified that way. I mean some signals can be considered to be an odd signal or an even signal. All right. So the definition of being an even function is the following. If these both have to do with symmetry. All right. So a function is even if it's symmetric about the y-axis. So that means that if x of t equals x of negative t for all t, that's a nice symmetry. An example would be something like, here's 0. Let's say here's the y-axis. It would look something like, let's say there. See how good at drawing I am? Okay. Oh, not quite, but that would be an even function. And an odd function would be, rather than reflected around the y-axis, if you rotate around the origin, and if it's symmetric that way, then it's odd. Mathematically, that says that function is odd if x of t equals x of negative t. Oh, sorry, that's what I already said above. If x of t equals negative x of negative t for all t. An example of an odd function, like I said, it's just now you have a symmetry, a rotational symmetry around the origin. So something like this. Let me try to. All right, that might be an odd function if drawn right. Okay. Great. So these seem like very narrow things to look at. I mean, why would you expect the signal to be even or odd? You probably wouldn't. However, it's kind of nice that you can decompose any function into the sum of an even part and an odd part. Sort of like we decompose any complex number into the sum of a real and an imaginary part. The formula actually looks very similar. So this is a unique decomposition. There's one even function and one odd function that together will make up any signal you're interested in. And so the even part, so what we're looking for is to represent x of t as the sum, as I said, the sum of an even part. I'll put a lowercase e down there for even, plus the sum of an odd part. That's what we're looking for. Of course, the even part should be even. The odd part should be odd, as the name indicates. Does anyone have a guess at how I will express this decomposition? Yes? No restrictions. None that I can think of. Yeah, should work. Can anyone think of a formula for extracting the even part? All right. Think back to how you found the real part of a number. Oh yeah, they are even and odd, and I wonder if I don't know a way to connect that to this, but the formula, if you do x of t plus x of negative t over 2. Okay, if you define that to be the even part, and look, it looks just like the formula we defined for the real part of a complex number, except instead of x of negative t, we had x conjugate. Right? And we can define the odd part to be x of t minus x of negative t over 2. Okay. Now, you can check, of course you should check, is this really even over here? And yes, it is. I mean, put negative t in. All you have to do is rearrange terms. You get back the same thing. Okay, so we could check that that's an even function. Put negative t over here, rearrange terms, and you get almost the same thing, but you get a minus sign. You put negative t in, and you say, oh, these are now out of order. Swap the order. Pull out a negative 1, and now you get the same thing back. Okay, so this will, in fact, be odd. This will, in fact, be even. And, of course, if we add them together, you get back x of t. Okay. I'm not going to verify all that if you want to do it on your own. But, it's just one-line arguments for each of those three things I said. And so any function can be decomposed into this even and odd part. So that's kind of fun. We won't use that early on in the course. At some point, we'll make some observations about what happens to even signals and what happens to odd signals. And it's nice to know that any signal can be decomposed into the two. Okay. All right, we have something else we want to talk about. A signal can be periodic. And what it means for a signal to be periodic is that it has some period about which it repeats. All right, so x of t is periodic with period t. Oh, actually, I want to do this. Well, let's say it's periodic if there exists a positive t greater than 0, such that it repeats at that interval. So we would say x of t equals x of little t plus this period, okay, for all t. So the little t's here are the argument of the function, and this big T is just some number. If it's always going to repeat after a certain duration, then it's periodic. Right? In other words, here's a signal. Suppose it looks like this. All right, I'll draw it this way too. Okay, suppose that's exactly repeating. All right, then it has a period of, let's say, this interval here to here. That's a period t. It's positive, and it satisfies this formula that any value you calculate, if you calculate that this value is going to equal, well, let's say this value here is going to equal the signal capital T later for any point. This is going to equal that. This is going to equal that. Okay, that's what it means to be periodic. And we would say with period, this periodic with period t. Okay, so it's periodic with period cap t. Now, there's more than one period with which this is periodic. Notice that if it's periodic with t, it's periodic with 2t. Okay, so any multiple of the period is also going to be a period. So we also want to know the fundamental period. The fundamental period is just the smallest period. We would say, usually you'd use you'd say T naught or something for the fundamental period, the smallest period of a signal. And you also sometimes you have a fundamental frequency. And a frequency is just an inverse of a period. So the fundamental frequency is, you might say that's F naught, and that's the inverse of the fundamental period. Okay. Some signals, well, first of all, notice I had to define, when you say periodic, this period had to be strictly positive, right? Because any signal would satisfy this for t equals 0. All right, that's always true for t equals 0. But we're looking for a positive t. Now, it may turn out that the smallest periods are all strictly positive, but the smallest one, mathematically you would say the infimum, if you have too many of these, could be 0. Can you think of an example of a signal where the fundamental period is 0? We said the periods have to be positive. Fundamental period 0. Constant. Yep. So if your signal is a constant, then any t is a period. Okay? That means the smallest period, well, is 0. So the fundamental period would be 0 for a constant. All right. You can actually come up with other crazy signals. For example, if you define the signal to be 1 for the rationals and 0 for the irrationals, you still get a fundamental period of 0. Okay, but we're not interested in those types of signals usually. Generally, the only time you're going to get a 0 period is if it's constant, if you're looking at smooth things. All right, and if it's not periodic, you might say the fundamental period's infinity if you use the definition of infimum. All right, not terribly important. some examples, of course, we know that sinusoids are periodic. So, for example, cosine of, now sometimes it's convenient to write cosine, the argument as 2 pi ft, because f will become frequency. We'll talk about that a lot more next lecture. Maybe you put a phase in there, some constant. Okay, so this type of a function, of course, sine can be expressed this way as a cosine if you give the right shift, right? Okay, so these are sinusoids. Okay, so, and these functions are periodic. And what is the period of this function? When does it? How far does it go before repeating? We know what this looks like, right? It's like, that's what a sinusoid looks like. The phi there is not going to determine its period. 1 over f. So 1 over f is, in fact, the fundamental period. There's no smaller period. Okay? So this is the fundamental period. Perfect. And my question was purposely ambiguous because I said, what is the period? There are many periods. 2 times 1 over f is a period. 3 times 1 over f is a period. Any integer, right? But this is the fundamental period. Of course, then that means what's the fundamental frequency? It's f. So in this way of expressing it, the fundamental frequency is f. Okay. There's a notion of a, hold on here. Oh. There's a notion of a discrete time signal and a continuous time signal. So let's start with continuous time. We talked about this a little bit last time. A continuous time signal is just some function defined over the real numbers. Okay, so its domain is some continuum, right? And a discrete time signal, its domain is the integers. And we actually often will write it with a square bracket. In fact, I'll use that to indicate to you that we're talking about a discrete time signal. Okay, these square brackets. And instead of t, I'll use n. Okay, so here, n is an integer. So in other words, a discrete time signal is a list of numbers, not a list that never ends, usually. Okay, we can actually consider finite, we don't have to consider signals that go on forever in duration. We can consider a finite list of numbers, which you might call a vector. Consider that a discrete time signal as well. Okay, okay. Now, it is also possible for you to have a signal. We try to distinguish what happens to its range. Notice these are statements about the domain. Okay. You could also talk about the range. Does the range hit any possible value? For example, here's a signal. Example signal. Let's say grades in high school math. Okay. Now, it's not a very interesting signal because it's probably just like constant A the whole way through. But let's imagine that it varied a little bit. Okay, so you might say, on this axis, this is the semester. Maybe there are 8 of them. 1, 2, 3 up to 8. And this would be a bunch of values. And to graph the value, let's do GPA instead of letter grade. Okay, so maybe it's a 2.3. We're really imagining here, and then it goes up to, a 3, and maybe at some point it's a 4. Goes back down to a 2. Okay, so we have some graph of your grades, right? Your GPA. Now, is this a continuous time signal or a discrete time signal? It's discrete time. It's a list, right? A sequence. There's no, I can't say what was your GPA at 1.5 or at semester 1.3. Okay. Now, in fact, this signal is, we could also try to specify something about its range. Its range can't take on any possible real number either, right? Because there's only certain GPAs you can get. A minus, B plus, maybe that hits 2.3, 2.7, something like that. There's only certain points it can hit. So this actually has discrete range as well, this type of signal. Sometimes you have a signal that would have been a continuous range, but so it's discrete time and it's also discrete values, discrete range. Not going to be the most important thing for us to think about. Discrete time versus continuous time, that's something we're almost always going to distinguish in this class. The range being discrete or not, we'll spend a couple of weeks talking about quantization, which is really going to be about that, the aspect of whether its range is discrete or not. Okay, but usually we won't care too much. Now, I want to, in the last few minutes, go through a little demo of using MATLAB because we'll get to play with some sound. We only have 4 minutes, so I have to do it quick. But this is sound is an example, and you're going to start your labs today. Please show up, do your labs starting this afternoon for some of you. And you get to work with sound. That's one of the frequent things you'll do in MATLAB. Of course, sound starts off as a signal that doesn't have a discrete range, right? It's a continuous time signal with a continuous range. It's air pressure waves or something that get picked up by a microphone. But at some point on their way into our computer and into MATLAB, two things happen to it. It gets sampled, okay, at certain periods of time, and it gets quantized. So the range is actually not just any possible number at each sample. Let me open up. It's going to be a bit rushed, but I think we can do it. So here's MATLAB. What I've done is I've written a little script that's in this window here. And this script does a few things. It uses a function in MATLAB to read an MP3. The MP3 I have it read is this one that comes as a demo in Windows. It's called Maiden with a Flaxen Hair. Okay, and so it's going to read it in and pass it to me as a vector, a long sequence of numbers. These numbers were the measurements. So let me run it just to make sure I've got it all going. Now these numbers, what I've done is I've plotted it here versus the index. Or actually, no, this is versus time. So I have 5 seconds of signal captured. You can hear what it sounds like. So to sound it, there's a function called sound. I give it back its data string, this x, this sequence of numbers, and I tell it what sample rate it was sampled at. That's 5 seconds of this beautiful song that they give you. And now what we can do is do some math to it. So we can do whatever we want. This is the beginning of signal processing for this class. You're going to define some mathematical function to change the sound. All right. For example, here's a few things just that really have nothing to do with what you're going to learn in this class. They're just like off-the-wall ideas of what to do. Okay. What if we as x2, what I've done is I've taken that sound and I've clipped it. What that means is that by using this min and max, I've said whenever the sound ranges from +1 to -1. All the data points, if I read them, like for example, if I look at x, the first value of x, okay, it's some number between -1 and 1. And x is just a big list of numbers. All right, and these make up that waveform that I've plotted. What I'm going to do, they go to plus or minus 1, but if I cut it off at 0.1, any value that was outside that range just gets cut down. This is what happens in like really bad speakers. If you blast them and they hit the edges, right? Then it's called clipping. And so we should hear something that sounds worse. Let's do X2. Sounds okay. I could clip it even more. Did anyone notice it sound different? Yeah. Okay. I could clip it down and make it really sound terrible. Let's do another thing. What if I just wanted to take these, let's say the square of every of the value at each point. So this is a weird thing. I'm not gonna play back the original numbers. I'm gonna square each number. I'm gonna get something that's always positive. So that's what we call X4 here. All right. Okay. One thing you notice right away, it's a lot quieter. Why is that a lot quieter? They're all between -1 and 1. You square them, they're going to get small. So you can use something to rescale them, sound scale. This will make it louder. You can hear. Okay, maybe we'll pull this open and do a few more next lecture. All right. You can go to any. We'll see after the first week which one becomes most crowded and deal with it. But yeah, you just need to demo some things to the TA that are listed on there. You don't have to be there for a designated time if you have it done.